Hello everyone and welcome back to my YouTube channel. Today we will see the most important topic in strength of material or in civil engineering or and in mechanical engineering. It's a very important topic as per strength of material is considered, that is known as a column and strut. So in maximum building construction we use column, and how to analyze the column when column will fail, today we will see through this lecture. So let's start the definition of column. Now column or strut is defined as a member of a structure which is subjected to axial compressive load. Now if I consider over here I will draw one diagram. Let's say this is a structure, and if this structure, let's say this is a three-dimensional structure, if this structure is subjected to an axial force, so here if you apply a axial force, then this member is called as a column, or we can say strut. Now you may ask me, sir, what is the difference between this column and what is strut? Then it's very simple. If structure or a member is a vertical, and if both the ends, now here if I consider this end and this one, if both are fixed one, then that structure or member is called as a column. Clear? Now if both the ends are fixed, now you already known in engineering mechanics what are the different types of fixed support, hinge support, roller support, pin support. Clear? Now if both the ends are fixed, then that is called as a column, and the position must be vertical. Clear? Now if you observe the vertical pillar between your roof and the floor, that is nothing but it's a column. Now next is, then what is a strut? Strut is also a member. However, if the structure is not vertical and one or both ends are hinged or pin support. Suppose this is another, if I draw another member, structural member, and if this structural member, if this structural member is not vertical, or if this end is free, then it is called as a strut. So this is a basic difference between the column and strut. Now this strut may be at any direction, however the column must be a vertical and both the ends must be fixed. Now for example, if you consider the strut, in that case you may consider the connecting rod, in IC engine. Clear? Or we can say piston rod. So if you observe the piston rod, both the end of the piston rod are pin type. So if you observe the piston rod, then if I draw piston cylinder arrangement here, if you observe, this is a piston. Now here if you observe the connecting rod, now this connecting rod, if you observe, it is fixed over here. Sorry, it's not fixed, it's a pin type joint, and again here you will observe the pin type of joint. Now this member is called as a strut. Clear? Now if you observe such cases, then we must learn the failure, how this failure of column. Now how the failure of this column may take place? Now as if we learn the compressive stress, if you apply a compressive force on any object, then obviously it will go for the compressive load. Clear? So failure of column may be because of the direct compressive stress. Clear? Now if the column length is more, if the column length is more, now here if I draw this diagram, so let's say this is one column, let's say AB is column. Now here if you observe, length of column is more as compared to lateral direction, then if you apply any force over here, then what will happen? It will start buckle. Clear? So it will start buckle. Then failure. So we learn the theories of failure. So in unit 6 video you may get the theories of failure. Failure means if the elongation is beyond the plastic limit, then it's called as a failure. So no need to break this entire column. Clear? Even though if it is go for the beyond elastic limit, then it's also called as a failure. Now we are learning failure of column. Failure of column maybe takes place because of the direct compressive stress. Next is because of the buckling stress. Clear? So because of these two, failure of column may occur, or we can say combined direct compressive and buckling stresses. Clear? So these are the failure of buckling stresses. Now what I will do, I will classify this entire column into main two types. Clear? So first I will say failure of a short column. Failure of short column. Now short column means if length is not that much more, then that column is called as a short column. Clear? And now if this column is applied or having or subjected to a compressive load, then obviously this particular column which is having very short length, clear, then definitely this will fail because of the crushing. Clear? So the column may be get fail because of the crushing. Now as we know the formula for crushing stress or compressive stress, that is compressive force divided by cross sectional area. Clear? So failure of short column is takes place because of the crushing only. Now next I will consider another case, that is failure of a long column. Now here I will draw the diagram. So if I consider this is a member, now this A is fixed one and this B end is free. Now this may be a column because it's a vertical. Clear? Now here if you observe, when you apply a compressive force at this end, clear, then what will happen? This may be get buckle. Clear? Now long columns do not fail by crushing. Now here crushing will not be takes place. Clear? As you apply the force, compressive force, it will start buckle. Clear? Now that will is nothing but it's a crippling load, or that load at the buckling start. What I'm saying, at the load at which load the buckling will start, that load is called as a buckling load, or we can say crippling load. Are you getting my point? What I'm saying, load at which buckling will start. So Here if you observe, buckling load is less than the crushing load, obviously. So if you want to fill entire this column, then we require large crushing force. Clear? But as the length is more, try to understand this concept. If you consider a small length column, then it need to fail due to the crushing only, and for that we require large compressive force. Clear? However, if length of column is more, now here if you observe, length of column is very large, at that time if you apply a small amount of force at the end only, then also it will start buckle, or that load is known as a crippling load, and obviously crippling load will be less than the crushing load. For short column it is relatively very high. So direct stresses will be applicable, and that stresses will be sigma 0, that will be P by A. Now stress due to the bending at the stress center. So what we need to evaluate? We need to evaluate stress due to bending at center. Clear? Now when you want to evaluate this phenomena, that is stress due to bending, then I will consider one column over here. Let's say this is A, at center I will consider B. When you apply force, it will start buckle, then this distance in this direction if I consider E. So when we apply the force over here, clear? So the entire column it will get deflected. The deflection is E. The value of deflection is E. Clear? Now if you recall the concept, that is this equation is known as the bending moment equation. Clear? Now here I will use these two terms, that is m by I equal to sigma by y. Clear? So from this sigma I can write moment into y divided by I. So sigma, that will be equal to m divided by, so here I will consider I by y. Clear? Now here I will write moment divided by z. Simple. So here we get this formula. Now what is moment? Moment is nothing but force into distance. So here I will write stress due to the bending at the center, that will be equal to P into E divided by Z. Simple. So Z is nothing but it's a sectional modulus about the axis of the bending. So this Z is nothing but sectional modulus, and it is given by I divided by y, moment of inertia divided by y. Clear? Now here if you observe, if you want a maximum stress, clear? Now in this case maximum stress, so this is bending stress, that will be equal to direct stress, that is sigma 0 plus sigma b, bending stress. And if you want minimum stress, then this will be the direct stress minus bending stress. Simple. Now column will fail when the maximum stress, which one? This maximum stress is more than the crushing stress. Clear? So this must be greater than the crushing stress. But in case of long column, the direct compressive stresses are negligible as compared to buckling stresses. Hence, for very long column, subjected to buckling stresses only. Clear? Now if you consider this case, when you apply a force, it will start buckle. It will not going to take a direct loading. Clear? So whatever this particular stress is there, we neglect. Clear? So in case of long column, we consider only buckling stresses. So I will consider only sigma b. Clear? So this is the difference between the long column, and short column. Short column fails due to the crushing stress, and long column fails because of the buckling stress or bending stress. And this bending stress, it is given by the formula P into E divided by Z. So that Z is nothing but it's a sectional modulus. Simple. So we will proceed further with the new topic, that is nothing but it's a assumption made in the Euler's column theory. So only two theories are important in case of column, that is Rankine's formula and Euler's formula, or Rankine theory and Euler's theory. Simple. Now, so when we consider the assumption, so first assumption is the column is initially perfectly straight and load apply must be axial. Clear? So initially it must be straight. Clear? And load must be axial. Clear? So here if I consider a cylindrical column, let's say this is a cylindrical column, then it must be perfectly straight, and load whatever you are going to apply, it must be at the axial. So at this center, if I draw the axis, then load must be axially. Clear? And this must be a straight one, it should not have any bend. Clear? Now next, cross section of the column must be uniform. What we require? Cross sectional. Now if I measure area over here, area at this section, area at this section, all this area must be equal. So that must be uniform. Third assumption is the column material is perfectly elastic, homogeneous and isotropic, and it must obey the Hooke's law. That is, up to elastic limit, stress must be directly proportional to the strain. Now why we are saying up to the Hooke's law only? Because after that any deflection will happen, that will be the permanent deflection, and that means it's a failure of that column. Clear? Now fourth assumption is the length of column is very large as compared to lateral direction. As we consider the long column, so whatever the length of the column is there, that must be very large than in lateral dimension. As I have considered cylindrical, then diameter must be less than the length. So less than must be far greater than whatever we have considered the diameter. Simple. Fifth assumption is the direct stresses is very small compared to bending. So whatever the direct stresses are there, that is P by A. So these are the very less than the buckling or bending stress. So we consider only these bending stresses as we discuss over here. Clear? So maximum stresses, that will be equal to direct plus bending, but it is very less. Why? Because as soon as you apply the load, it will start buckle. Instead of taking any axial load, it will start buckle. So its direct stresses are very negligible, or it's a very less value. And last but not least, most important is whatever the self weight is there of column, it must be negligible. Clear? So these are the different assumption we have made before learning Euler's theory for the column. Now second one is important is sign convention. Clear? So if I consider the column fixed at one end, and if I consider the initial position of this column, let's say B, and if this once we apply a force on this particular column, then column will bend like this or like this. So if I consider B dash or B double dash, then if you observe both the cases, then convexity will be there. So in such cases, if in this such cases, if such buckling will takes place, then that I will consider as a positive. And if I consider both pin joint, so here one end is free, so this end was free and this end was fixed. So when you consider the column, let's say this is point is A, so A and B. Now if you observe here, I have considered the pin point instead of the free and fixed. So in this case what will happen, this column will bend in such fashion. Clear? Now either this or this. Clear? So this will become a concavity. Clear? So such thing we consider as a negative. Simple. So this is the small information which we need for the Euler's theory. So most important theory for the column we will see over here. So I will write expression for crippling load when both ends of the column are hinged, or we can say pin. I hope you understand the different types of supports: fixed support, hinge support, free support. Clear? Now here I will consider one column. So here what we have considered, pin support. So here this is A end, this is B end. So once we apply a force P, then what will happen, this column will bend. Clear? This column will get bent. Now if I consider the distance, so let's say up to this distance I will consider, so this distance I will consider as a x, and this distance I will consider as a y. So this point I will consider C, and if up to B to A, so this is nothing but it's a length of the column. Simple. Now here if you observe moment due to crippling load. What is crippling load? Load at which buckling of the column will start. Now that is very simple, that is force into distance. Clear? So that is equal to force into distance. So here I will write, instead of E I will write Y. Clear? Now here if you observe, so this is a concavity, this is also a concavity. So here I must consider the negative moment. Simple. But as we know, moment is nothing but that is the value, that is EI d square y divided by dx square. Simple. So from equation 1 and 2, if I equate, then I can rewrite both the equation are ei d2y divided by dx square, that will be equal to p into y. If I take in this direction, then I will get d2y divided by dx square plus p into y, that will be equal to 0. Simple. Now I will again simplify d2y divided by dx square. I will divide entire equation by ei. So this will become p divided by ei into y equal to 0. Simple. Now again I will simplify d2y divided by dx square plus alpha square into y equal to 0. Now you may thinking that what is this alpha square? So I am considering alpha square equal to p divided by ei, or in alpha I am writing under root of p divided by ei. Now this is a very much well known expression. Second order derivative equation is in front of you, and the solution of this above equation, so it will be give is equal to y equal to c1 into cos of alpha x plus c2 into sin of alpha x. Simple. So I am writing the value of alpha. So y equal to c1 into cos of under root of p divided by ei. So this value, alpha value, ei into x plus c2 into sin of under root of p divided by ei into x. Simple. Now here if I consider the value, so this is then distance along vertical direction, x is there. Simple. So at a x will be 0 and at b x will be equal to l. So I will write at a x will be 0 and at b x will be equal to length of column. Simple. So I will put first condition, that is at a, if you observe, x will be 0 and y will be equal to 0. If you see, maximum deflection is at center, at this end and at this end. At both the end, if you observe, at a x is equal to 0, y will be 0. X is equal to l, but y will be again 0. At center you will get the maximum deflection. Simple. So if you put in this equation, let's say this is equation 3, then y will be equal to 0, then c1 x will be 0. Simple. And then cos 0, so this will become cos 0 plus c2 into sin 0. So as we know, sin 0 will be 0 into c2 equal to, sorry, if you multiply 0 with c2, then it will become 0. Simple. And cos 0 is 1, so 0 equal to c1, so value of c1 will become 0. Now I will put a second condition, that is at b. So at b x will be l, however y will be 0 and c1 value will be 0. So from equation 3 I can rewrite y will be 0, and as the c1 0, this entire expression will become 0. So c2 into sin of under root of p divided by ei into l. Clear? Now here if you observe, there are two terms are there, that is c2 and sin under root of p divided by ei into l. Simple. Now either C2 will be 0 or this equation will be 0. Now if I consider C2 equal to 0, if I consider C2 equal to 0, then what will happen? This entire equation y will be equal 0. Why? This C1 is already 0, and if you put C2 equal to 0, then entire expression will become 0. Means at any load, deflection will not be there. Whether this will happen for a long column? Answer is no. Clear? That's why C2 will not be equal to 0. Are you getting my point? Then if C2 is not equal to 0, then what will be the equal to 0? Then definitely this sine L into under root of P divided by EI, this expression must be equal to 0. So at what uh, what value sine will be 0, then I can say that sine 0 will be 0, sine 0 will be equal to 0, sine pi will be equal to 0, sine 2 pi again it will be equal to 0. So there is some terms, so obviously sine pi, and limiting value is nothing but it's a pi. So I will write this entire expression and that will be equal to pi. So sine pi will be equal to 0. So from these two equation, let's say this is 4 and 5, from this equation 4 and 5 I can rewrite L into P divided by EI, that will be equal to pi. Simple. So if I take this L in that direction, then I can rewrite P divided by EI equal to pi by L. Simple. Now I will take square of both the side, then P divided by EI, that will be equal to pi square divided by L square. Simple. So if I want to evaluate the crippling load, so this is P is nothing but buckling load or crippling load, then I will get formula, that is pi square EI divided by L square. So this is nothing but it's a Euler's formula to evaluate or to get the crippling load. Now in this expression, if you observe, there is an I, moment of inertia. So you might have evaluated Ixx and Iyy. Clear? Now what we need to take? We need to take the least value of Ixx or Iyy. Simple. Smallest value of Ixx and Iyy. Why? If you consider the smallest value of Iy, then deflection will takes place. That's why that I is nothing but it's a least value between this Ixx and Ixy. Simple. Now this in this expression, if you observe, this expression we have derived for the hinge or pin support. So we started with the hinge and pin support. Now there are different types of supports are there. One end may be fixed, one may be free, both end may be pin, one end may be pin, one end may be a fixed one. So for that purpose, what we required a uniform formula. Simple. So if you derive for that case also, then if you observe this one end is pin, another end is fixed. So here again we need to consider the positive moment. So this one P into Y. Again if you derive, then we get the different equation for the crippling load. Clear? Now for that purpose, what I will do, I will consider the effective length. Effective length, or it is also called as a equivalent length of a column. Simple. Now the effective length of a given column with given end condition is the length of an equivalent column of the same material and same cross-sectional area with hinged end and having the value of crippling load equal to that of the given column. Whatever the condition we are assuming or equaling the length, that is nothing but when the pin or hinge support is there, that length is called as a equivalent length. And for that purpose I will rewrite the formula, that is crippling load equal to pi square into EI divided by LE square. Simple. So here you can use this one, is a standard formula, Euler's formula for long column. Simple. Now if I consider the different condition means end condition of column, and here I will write relation between effective length and actual length. Clear? So I will consider a different condition. So first condition is both ends hinged, or we can say pin. At that time this L will be equal to L, as we have already defined. Effective length means when column is having both ends are pin joint or hinge joint. Next one, if I consider one end is fixed and one is free, at the time we can say LE equal to 2L. We consider always this formula, but while putting the formula, and if the condition is one end is fixed and one end is free, one end is free, at the time we consider effective length equal to 2L. So likewise there is another third condition is there, that is both ends fixed, at the time LE will equal to L by 2. Fourth condition is there, last condition, that is one end is fixed and other end is hinged. Clear? So at that time we use formula L equal to under root of LE equivalent length equal to L by under root of 2. Simple. So you might thinking, sir, how you are writing this one? If you derive using the different end condition, then you will get the different values for the crippling load, and if you compare that also with this equivalent length, then we will get this value. Simple. So I hope you understand this concept. Now we will move further. We will see some topic, interesting topic. Now here I will consider crippling stress in terms of effective length and radius of gyration. Now this term radius of gyration you might have learned in engineering mechanics. Clear? So if I want to evaluate the moment of inertia, then this moment of inertia is nothing but second moment of area. So if I want to write in terms of radius of gyration, that is nothing but if a distance, so this is a distance. Clear? This is an area. Clear? So this we can say equivalent distance. If there are n number of particles are there in a system, and when we consider the moment, at that time we consider x1, y1, y2, y3, y4 instead of all the distances. If I write one distance only, then that is called as the radius of gyration. You may get a better definition in engineering mechanics. Clear? Now here what we learn, moment of inertia must be least. Clear? So for that purpose we must consider the least value of radius of gyration of the column. So if I consider the crippling load formula, that is pi square ei divided by le square. Clear? Now here I will write, instead of I, pi square e into a into k square divided by L square. Simple. Now here this k square I will divide over here, then I will write same formula, that will be equal to pi square e a divided by L e divided by k whole square. Clear? Now if I consider the crippling stress, so this is crippling load, and if I consider the crippling stress, then I can write force divided by area. So if I consider the force value, whole square divided by area. Simple. Now this area and this area, it will get cancelled, and then I can write crippling stress, that will be equal to pi square e divided by le divided by k whole square. Simple. Sorry. So from this formula I am getting another term. Clear? So the term is nothing but it's a slenderness ratio. Slenderness ratio, and this is nothing but it's a ratio of equivalent length divided by the radius of gyration. Simple. So this is all about the Euler's formula. Clear? Now again I will write, or we will discuss some limitations of Euler's formula. Clear? Now if you observe this Euler stress formula, that is P equal to pi square EA divided by LEK whole square. Simple. Now when the slenderness ratio, that is Le by K, when this slenderness ratio is small, then what will happen? This particular crippling load, it will be very high. However, crippling stress cannot be greater than the crushing stress. As we already learned, crippling stress cannot be greater than, this should not be happen greater than crushing load. But in this case, if you observe, if this value is very less, at that time the stress, the crippling force, it is much more greater. So crippling stress is also a greater. So from this equation we can get the crippling stress. So if this is very less, clear, so this will be very high. So why this happen? When this slenderness ratio, that is Le by K, when this will be very less, if this effective length, or we can say length, is very less, and if when this value, which one, length value is very less, then that is called as a short short column. Clear? So this particular Euler's formula cannot be used for the short column. It is only used for the long column. Clear? So if long column is there, then length is more. If length is more, then this factor will not be very less. If this is more, then definitely the crippling stress or load, it will be less than the crushing load. Simple. This is all about the limitation of Euler's formula. Now when this point got by the Rankine, then he evaluated Rankine formula. This is an empirical, so by using trial and error, by doing more experimentation on the column, he derived one empirical formula. So that formula I will rewrite. I will write 1 by P equal to 1 by PC plus 1 by PE. Simple. So in this equation, P is nothing but it's a crippling load by Rankine. Simple. It's a crippling load by Rankine. Now PC is nothing but it's a crushing load. Crushing load, and it can be given as crushing stress into area. So it is used for the short column. Simple. It is used for the short column. 1 minute. Now if I consider the PE, now this P is nothing but it's a crippling load by Euler's formula. Clear? So this is the equation or empirical relation. Now let's see how this formula is useful for the different condition. Now first condition I will consider over here. If column is short, clear? Then what will happen? Column is short means L is very small. Simple. L is very small. Then in that case what will happen? P will be more. Clear? Then the value of P, so I will write P by Euler's formula, that is pi square EI divided by L square. Now this is very less, then this will be very high. Clear? So it is inversely proportional to, when this will less, length will be less, then this will be very high, and if this is very high, then the factor which we use in Rankine formula, that will be very less. Clear? So this 1 upon P, it will be very less. So at that time what we will consider? Crippling load, that will be depends upon only crushing load, and this crushing load can be given by crushing stress into area. Simple. That's why if the column is short, then it failed due to the only crushing. Simple. So this is the relation through which we can say that short column will fail due to the crushing only. Simple. 1 upon PE factor, it is very less. That's why we neglect the buckling load for short column. Second condition is there. That second condition in which we consider long column. If column length is long, then definitely LE will be very large. Then if I write P formula, that is pi square EI divided by L square. So if this L square is very large, then this value will be very less, and if this value is very less, then 1 upon PE, this value will be very high. Clear? So for long column, crushing force or crushing load we neglect. Clear? That's why 1 upon p, that will be equal to 1 upon p. Simple. So for the long column, hence ranking formula, it gives better result for short column as well as long column. That's why we use ranking formula for both the cases, for short column as well as for long column. Simple. So I will rewrite this formula: 1 upon p equal to 1 upon pc plus 1 upon pe. So if I take common pc into pe, then I can write pc plus pe 1 upon p. Now if I take reciprocal of this, then I can write p equal to pc into pe divided by pc plus pe. Simple. Now here I will consider pe common. Then here pc into pe, then I will take pe common. So I can write pc divided by pe. So pe get cancelled. Then I will get p is equal to pc divided by 1 plus pc divided by p. Simple. Now I will put the value for the crushing load, that is nothing but it's a sigma c into a divided by 1 plus sigma c into a divided by pe. Now we have form value for p also. Instead of p, can we write this pi square ei divided by l square, and instead of this I will write ak square. Definitely that k value will be very, sorry, that must be a least value. Clear. So I will write sigma c into a divided by 1 plus sigma c divided by pi square into a into l square divided by ak square. Simple. Now this a it will get cancelled. So crippling load, I will get sigma c into a divided by 1 plus sigma c divided by pi square e into l by k whole square. Simple. Now instead of this sigma c pi square e, I will write alpha, and I will write load, crippling load, that is equal to sigma c into a divided by 1 plus alpha into le divided by k whole square. So this is the expression to evaluate the crippling load by ranking formula. Clear. Where alpha is nothing but ranking constant and its value is sigma c divided by pi square e. Clear. And if you want to evaluate the load by Euler's formula, then that is p is equal to pi square ei divided by le square. So for different condition, le value will be different, that we already learned. Simple. Now this Euler's formula, it is used for only long column, but ranking formula, it is applicable for short column along with the long column. Clear. I hope you understand the concept of concept of column and strut, how it fails, ranking formula, Euler's formula, assumptions of Euler's formula, and then we learn the ranking formula. In that we also learn the slenderness ratio also. Clear. So in this way we finish the column and strut. Clear. So I hope you like this video. If you like this video, then please subscribe my channel. Thank you so much.